Welcome to the class. Dear students, today we are going to discuss on Wolff-Kischner reduction. So in this video session, we are going to see what is a small introduction on what is Wolff-Kischner reduction. Then we will see the reaction. Then we will go for its mechanism. And finally, we are going for its synthetic utility. So let us start Wolff-Kischner reduction. So Wolff-Kischner reduction is a method to convert aldehyde and ketone into its corresponding alkane. Okay, so aldehyde and ketone converts into its corresponding alkane or corresponding hydrocarbon. And in this method we use a base as catalyst. So it is basically a base catalyzed conversion of aldehyde and ketone into its corresponding hydrocarbon or corresponding alkane. Okay. By meaning, so what is the two things? It is from this statement, it is very evident that the raw material is aldehyde and ketone. Aldehyde and ketone will show Wolff-Kischner reduction. Only aldehyde and ketone. And the product that is formed is alkane. Its corresponding alkane. And the catalyst is a base. Okay. When I say that base is used as a catalyst, what I mean is that the reaction actually doesn't need a base. It will proceed by itself, but at a very slow rate. Okay, it will proceed at a very slow rate. If you are using base as a catalyst, what will happen that the reaction speed will increase, the rate of the reaction would increase, and you would get the alkane at a very faster rate. Okay. The second thing when I say that I use base as a catalyst is that it doesn't form the catalyst base, it doesn't form a part of the product. Okay, at a particular point it gets out of the product and it is recycled back into the reaction. So that is the meaning of a catalyst, right? A catalyst doesn't form a part of the product, it is recycled back into the reaction system. So that we will see in the reaction mechanism, how it is recycled back and how it increases the rate of reaction. All that we will see in the mechanism. The second most important point that I want to tell to you is that only those aldehyde and ketone that are stable in basic conditions, only those aldehyde and ketones will show the Wolff-Kischner reduction, or only those aldehydes and ketones will give corresponding alkanes in the presence of that strong base. Okay, so the Wolff-Kischner reduction is only shown by those aldehydes and ketones which are stable in very basic conditions. That is the second point that I want to tell. The third thing that is very important is, as this conversion takes place, now as aldehyde or ketone, it gets converted into alkane. As this conversion takes place, it occurs at the expense of nitrogen gas. That is, evolution of nitrogen gas takes place simultaneously with the conversion of aldehyde and ketone to corresponding alkane. I hope these 3 points are very clear to you. Now let us come to the reaction itself. Let me write the reaction first and then we will go for its explanation. So in this reaction, we are treating a carbonyl compound with hydrazine. So here the carbonyl compound that I am taking is acetone. So this is acetone. I am reacting acetone with hydrazine. So this is hydrazine. Okay, and the product that I get is hydrazone. Hydrazone. And this on treatment with a strong base like KOH, or you can use C2H5ONA. Anything you can use. In some books it is written C2H5ONA, sodium ethoxide. In other books you will see potassium hydroxide. Anything you can use. So I am using here KOH. No need to write this. Okay. Then what will occur? What will happen? It will lead to alkane. So as you can see here, there are two major steps in this reaction. The first step is the formation of hydrazone by reaction of carbonyl compound with hydrazine. The formation of hydrazone, that is the first step, major step in the reaction. So the first step is the formation of hydrazone by reaction of carbonyl compound with hydrazine. Second major step is the conversion of hydrazone in the presence of a base as catalyst into corresponding hydrocarbon or corresponding alkane. The second step is the conversion of hydrazone in the presence of base as a catalyst to corresponding hydrocarbon or alkane. So you can see that there are two major steps in this reaction. The first is the formation of hydrazone by reaction of carbonyl compound with hydrazine. Second step is the conversion of hydrazone in the presence of base as a catalyst into its corresponding alkane. These are the two major steps of this reaction. We will understand this reaction in a very much better way by looking at the mechanism. So let us look at the mechanism. The mechanism actually, it is a subset, it's a substeps of reaction, right? In this we divide the reaction into number of substeps, correct? So let us see, there are 5 steps in this mechanism. Step number one, formation of hydrazone. You now know what to react with what to form hydrazone. We have already shown. You take the carbonyl compound. Here we are taking acetone, and you react it with hydrazine. You can write the lone pair of electrons on nitrogen. It has one lone pair of electron. You can show them both on both the nitrogen. Just make hydrazone like this. Just make a hydrazone. That's it. Hydrazone. This is the acetone or carbonyl compound. It reacts with hydrazine to form hydrazone. Now we will try to understand how this product is formed. You can just note down first the reaction, and now we will try to explain how this is formed. Okay, just note down this reaction. Okay, now let us try to understand how this is formed. Okay, now just look at this structure. Okay, this is the carbonyl compound. Here this carbon double bond O, this bond double bond is highly polarized. This is polarized because oxygen is electronegative and carbon is electropositive, and therefore the shared pair of electron here, it is always towards the oxygen side. It is always towards the oxygen side, and therefore the area around oxygen is always negative. And because it is away from carbon, the area around carbon is always positive. Now, playing into this opportunity is hydrazine. How hydrazine plays into this opportunity? Hydrazine, there are 2 nitrogen atoms which is having lone pair of electron. So it can very well act as a Lewis base. Correct? A Lewis base is something that can donate a pair of electron. So what can happen here is that the nitrogen can donate a pair of electron here to this positively charged carbon. So the structure that we get is something like this. It will be like this, like, right? Because I am putting this arrow because a pair of electron is getting donated by nitrogen. So it is a coordinate covalent bond. Therefore I am putting this arrow. These are the 2 hydrogens of this nitrogen, and it is connected to NH2 here, right? And what would happen? Yes, this would be the structure. Now what happens here, that nitrogen has donated its lone pair of electron to carbon. Because nitrogen has donated its lone pair of electron, the nitrogen becomes positive in charge, right? And when it donates this lone pair of electron to carbon, carbon's valency, it is actually right 4. So this pair, what carbon loses is the pi electron pair to more electronegative oxygen. Right? This pair, it goes here. When nitrogen donates the pair of electron here, this pair of electron, it would go to oxygen. Okay, the pi pair would be lost to the more electronegative oxygen like this. Right? Yes. Now look at the situation of this nitrogen atom. Nitrogen atom is electronegative. Correct? These both are electronegative. This is also electronegative, I agree. Nitrogen atom is electronegative. Its electronegativity is further enhanced by a positive charge over it. Right? If there is a positive charge on nitrogen atom, electronegativity will further increase. Okay. So nitrogen needs to take electron from somewhere. It can't take from this nitrogen because this nitrogen is also electronegative. So it can't take from this nitrogen. It can't take from this carbon because carbon is attached to another electronegative atom which is pulling its electron. So it can't take from this carbon. The only option that it has to take electron pair from this hydrogen and to eliminate this hydrogen out. Right? And this electron pair which it has taken from hydrogen, it can be given to carbon. And this electron pair which has been donated to carbon, it can be taken back and it can come back as lone pair. Correct? And this can come here. Right? And this H which has been eliminated, it can go and attach here. So the new structure that you get will be something like this. It will be like this. Right? There will be a lone pair will come back and NH2 will be here, and there you go, OH. O also has two lone pair of electron. Correct? Yes, you can show that too. Now we get this we get a structure like this. Now just see, do you think that this nitrogen's demand has been fulfilled? Totally no. There is still problem. This nitrogen is electronegative. Its electronegativity is further enhanced by the presence of this nitrogen atom. This nitrogen atom is also electronegative, so it has an electron pulling effect from downstairs. Right? This carbon is attached to electronegative oxygen, so this carbon is also a little bit of electronegative in nature. So nitrogen is under already pressure, and over and above it, nitrogen itself is electronegative. So you can say that everywhere this electronegative pressure is coming. So it would take the electron pair from this hydrogen towards itself, and with the result this hydrogen would also go. Now this hydrogen has another option. It can go and attach to the lone pair of OH. So when it attaches to the lone pair of OH, one of the lone pair would be taken and O would become positive because one of its lone pair is lost. When hydrogen went and attached to the lone pair of oxygen, the electron pair was left here, right? So that electron pair would come here. Right? So that would be the new structure. Right? Now what can result? You can yourselves judge. To eliminate the positive charge, to eradicate the positive charge, this electron pair is taken by the electronegative oxygen, which electronegativity has been more enhanced by the positive charge over this. So this electron pair would be taken by this oxygen, no doubt. That would relieve it of its positive charge. So when that is taken, what would be the result? This carbon would lose an electron pair and H2O will be formed. And this carbon would become positive. Correct? Now what can happen? This electron pair, it can come here. When this electron pair come here, the carbon loses its positive charge and this would be the result. So now you get what? Hydrazone. Fine. So that is the way we get hydrazone here. Fine. This one. So that is what we have written in the first step. You already have noted, I have just shown how we got this structure by these explanations. There are two substructures here that come in between. So we have got this idea. Let us now go to step number 2. So now we have got hydrazone with us. Now let us go for step number 2. What is step 2? Let us see. Step number 2, formation, your abstraction of proton by base, abstraction of proton, or you can say deprotonation of nitrogen, deprotonation of nitrogen. This is the first deprotonation of nitrogen. Okay, this is the first deprotonation. Let's write the hydrazone first. This is the hydrazone that we have got. You get N here, right? This H2, you can write it like this. Now base acts. We have used KOH in the reaction. OH minus is a very strong base. It would not wait. It would knock out a H from here. Correct? When it knocks out a H from here, what would be result? What would be the result? Yes, this would come. Correct? When it knocks out a H from here, this has an H hydrogen. When it knocks out a H from here, this becomes a negative charge over here and hydrogen is still here. So this would be the result. Now this negative charge, it can come between two nitrogen. When it comes here, nitrogen valency is actually 3. So this is over it. So this electron pair would come here. So now, because nitrogen can accommodate maximum 6 electron. So when it comes here, it would become 8 electron. So this pair of electron would go back to carbon. Fine. So now what you get is a carbon anion. A carbon anion structure you will get. So deprotonation of nitrogen will lead to formation of carbon anion. What has happened in this step 2? OH minus, the base, has knocked out a proton from the nitrogen. When it knocks out a proton from nitrogen here, the terminal nitrogen becomes negatively charged. To eliminate its negative charge, it comes as a pair of electron as a bond between these two nitrogen. Now nitrogen here can accommodate maximum of 6 electrons, but here there are 8 electrons. So this pair of electron would go here and a carbon anion results. Now let us see step number 3. Step number 3, protonation of carbon anion. Protonation of carbon anion. I forgot to tell you that when in this step, in step number 2, we have seen that OH minus knocks out proton, the OH minus, it was knocking out a proton. Correct? When it knocks out a proton, what would be the result? It would become H2O. Please keep that in mind. Okay, we are going to use this H2O in third step. Fine. So now let's go to step number 3. Step number 3. Protonation of carbon anion. Protonation of carbon anion. Let us see what happens in this. We will draw the product of step 2. What was the product? This is the product C, correct? Minus N, double bond N and H. Am I right? Now what would happen? As I told you, in step number 2, OH minus knocked out a proton from hydrazone and it became H2O. So you have to write this H2O here This is the H2O. Am I right? Yes. Now this carbon anion is actually a very strong base. A very strong base. It can donate a pair of electron. Okay. So now water is amphiprotic in nature. Am I right? It's amphiprotic in nature. That means when it sees a base, it acts as an acid. And when it sees an acid, it acts as a base. So here it encounters a base. Therefore here water will act as acid. It will act as a Lowry-Bronsted acid, donating one H plus. Am I right? Yes. And what would be the result? OH minus would come out. Correct? Yes. So H plus will be donated. The water will act as a Lowry-Bronsted acid, and this carbon anion, it acts as a Lewis base. Fine. So now we get a structure like this, CH. Correct? Yes. So here we go. We got a structure like this. And the result is OH minus. Please note this OH minus. We are going to use it in step number 4. Okay. I hope you understand. Now let's go to step number 4. Step number 4. Step number 4 is deprotonation of nitrogen. Deprotonation of nitrogen for second time. Of nitrogen for second time. Okay, there is another another hydrogen atom attached to the terminal nitrogen. Now that will be knocked out. Let us see what we are trying to say. So this is the product of step number 3. Now there is a hydrogen atom here, right? We got OH minus in step number 3, right? That OH minus, we will use it here. Okay, it plays a role here. What OH minus does, it's still a very strong base. It can knock out the H from here, and the product that we get is this. Correct? When it knocks out a H, what it would become? It would become H2O. Please note this H2O we are going to use in step number 5. Fine. Now this is this thing. Now this negative charge is not stable here. It would come as a bond pair. When it comes as a bond pair, this becomes N triple bond N. So N triple bond N means N2 as an entity. Okay, there is 3 valence electron in one nitrogen. It needs 3 more electrons. If it gets 3 more electron from another nitrogen atom, it would go as N2. Correct? So you go as N2, and when it goes as N2, this pair of electron is not needed now, so it goes here. So you get another carbon anion. You get another carbon anion like this. I hope you got it. So let us see what happens here. Here again the OH minus that we got in step number 3, here it plays a crucial role. What it does is that it knocks out a hydrogen from here, okay, H plus from here, and becomes H2O. This pair of electron now comes here as negative charge. This is not stable. So this jumps here and becomes a bond pair between these 2 nitrogen atoms. Nitrogen valency is 3, correct? It is 2p3. So it needs 3 more electrons. So if it gets 3 more electrons from another nitrogen atom, it can very well become N2. But in the process of becoming N2, what happens is that this pair of electron is left with carbon. That leads to formation of another carbon anion. As I was saying in the introduction, all these things, conversion happens with the evolution of N2 gas. Correct? So that thing is now clear here in the mechanism. The conversion is happening in the presence of N2 gas. It now needs 1 more H to become a hydrocarbon. This is step number 4. Please do make note of H2O. We are going to use in step number 5. Let us now see step number 5. Step number 5. Step number 5 is protonation of carbon anion. Protonation of carbon anion. Step 5. Protonation of carbon anion. Let us see what happens here. So you draw the product that you have got in step number 4. This is the product that you got in step number 4. Right? And you draw what was the byproduct that you got? Yes, water. You draw that water here. Now this is a carbon anion. It acts as a very strong Lewis base. It wants to donate its pair of electron, and in the presence of water is amphiprotic in nature. As I have already said, it acts as base in presence of, it acts as an acid in presence of a strong base. So now it is acting as a Lowry-Bronsted acid. It would give H plus here, and the net result is this thing, an alkane, right? So you can rub this and simply write CH2. You formed an alkane, and one more thing that I want to tell to you, you got the catalyst back. So base acts as catalyst. We have said this when we started the reaction in introduction part, that you will get the catalyst back and that we will understand it in mechanism. We also said that it happens with the evolution of nitrogen gas, and in step number 4 we have seen that how nitrogen gas has evolved in this formation of hydrocarbon or in the formation of its corresponding alkane. So this is the way an aldehyde or a ketone converts itself into its corresponding alkane in the presence of base as a catalyst. Okay, all this occurs by reacting it with hydrazine and the intermediate formation of hydrazone. The synthetic utility, let's come to the synthetic utility. Synthetic utility, you can make alkane derivatives and alkanes using carbonyl compounds. Using carbonyl compound, that is, if you are using aldehyde and ketone, you can make its alkane and alkane derivatives. Okay, this can be the final products of a reaction, or it can be intermediates of a reaction. Dear students, we have seen Wolff-Kischner reduction, we have seen the mechanism, and we have seen the reaction itself. We have seen how carbonyl compounds convert itself into corresponding alkanes or corresponding hydrocarbons. All this occurs because we have treated it with hydrazine to form corresponding hydrazones, and that hydrazone was subjected to very strong basic conditions. In the process, we have seen that N2 gases evolved, and in the last step we have seen that OH minus, it plays a role of a catalyst. It recycles back into the reaction. We have seen all this. Dear students, I hope you have liked the session, you have understood the class. If you have done so, if it is useful for you, please do not forget to subscribe the channel, do like and do share the video. Thank you very much.